All right, so let's do some examples from the day 13 assignment where we're solving quadratic equations, but we're going to have to use some other methods. Like, for instance, here they want us to solve by completing the square. For future reference, completing the square isn't the most efficient method. Anything that can be done completing the square, we can use quadratic formula. But for the purposes of instruction, I do need to show you how to complete the square. So that's why we're going to go ahead and do it this way. X squared plus 6x is equal x squared plus 6x plus 11 is equal to 0. So the first thing I want to do is check and see if maybe I have a perfect square trinomial. Perfect square trinomial is a trinomial, 3 terms, where the first and last terms are perfect. This is actually why I don't have one. It's because 11 is not a perfect square. But if it was though, the middle term, the b, would have to be equal to 4 times a times b squared would have to be equal to 4 times a times c. But we don't even get that far because 11 here is not perfect. So my first step is going to be to move any constants to the other side. In this case, by subtracting 11. X squared plus 6x is equal to negative 11. Now, I need to make sure that my first term is perfect, which it is. X squared is a perfect squared. It's x times x. So because of that, I can now go ahead and complete the square. Because a out here in front is a 1, I could use the b over 2 squared formula for completing the square if I'd like to. But just for consistency, I like to use b squared over 4a. So that would be 6 squared divided by 4 times 1, which is 36 over 4, which is 9. So what I do now with that number is I want to add that number to both sides. I'm going to write the x squared plus 6x that I had before, and then I'll add 9. And that's equal to the negative 11 that I had before, but then also plus 9. By completing the square, I'm now guaranteed a perfect square trinomial. At the beginning, I didn't have a perfect square trinomial, but now I do. X squared and 9 are both perfect, and 6 squared is equal to 4 times 1 times 9. So the reason why I want a perfect square trinomial is so that I can factor. Automatically, every perfect square trinomial is going to be factored as one parentheses with a square on the outside. I'm going to keep the sign in the middle. That's going to drop into the middle of my parentheses. And then on each side, I'm going to have the square root of each perfect square. So the square root of x squared is x. The square root of 9 is 3. And that's equal to negative 2. Negative 11 plus 9 is negative 2. Well, now for the first time, my equation only has a single x, which means I can now use square root property. I couldn't use square root property before because I had x squares and x's, and those couldn't be combined. But now I only have a single x that's inside here. And so I need to be able to get to that x. So I'm going to now take the square root on both sides. I'm going to use square root property, which tells me that x plus 3 is equal to the square root of negative 2, which the negative comes out in the form of an I. The 2 is prime, so that stays on the inside. And of course, I can't forget cardinal rule. I need the plus or minus. Now one last step, because x is not isolated yet. Now really with a plus or minus, I'm supposed to break this up into 2 equations and say x plus 3 is equal to I square root of 2, and then on a separate equation say x plus 3 is equal to negative I square root of 2, and then continue to solve. But since the only step left to do is subtract, and I'll never be able to subtract or combine a rational number with either an irrational number, which is the I, or with a radical for that matter, for any of those, I won't be able to actually combine them. I can just leave it as 1 and say x is equal to negative 3 plus or minus I square root of 2. So because of the I, my solutions are not real. Negative 3 plus I square root of 2. negative 3 minus I square root of 2. And that's correct. Okay, here they want me to complete the square again. Now here I already have the constant on the other side, so all I got to worry about now is completing the square, but the problem is that 7 is not a perfect square. So there's two options. Most books would tell you to divide everything by 7, because if you do that, then 7 divided by 7 is 1, and you'll have a perfect square out in front. But now that's going to cause fractions, because now you'd have to have a 15 over 7x and a 4 over 7, which you might not want to deal with. So in order to try to minimize the effect of, sometimes you can't avoid fractions, you're going to have to deal with them no matter what, but in order to try to minimize that, instead of dividing by the lead number, we can also multiply. So that gives me 49x squared plus, that's going to give me 105x is equal to 28. Well, now I can go ahead and complete the square. 49x squared is perfect, so I can use my formula then. And say 105 squared over 4 times 49. 105 squared is 110.25 over 49 times 4, which is 196. That could be reduced. I don't think that can be divided, but that can be reduced. Into 225 over 4. They can both be divided by 49 and gives you 225 over 4. So that's what I'm going to have to add to both sides. We'll have 49x squared plus 105x plus 225 over 4 is equal to, I'll write 28 over 1, because I know I'm going to have to add a fraction, plus 225 over 4. Here I'm guaranteed my perfect square trinomial. I'll keep the sign in the middle, which is plus. The square root of 49x squared is 7x. The square root of 225 over 4 is 15 over 2. Because the square root of 225 is 15, the square root of 4 is 2. And that's going to be squared. It's always squared, and that's equal to, the LCD here is 4, 225, and 4 times 28 is 112. So I have 7x plus 15 over 2 squared is equal to 337 over 4. I'm going to take the square root on both sides. 7x plus 15 over 2 is equal to plus or minus. 337 is a prime number, so even if I were to try a tree, it wouldn't work. And the square root of 4 is just a regular 2. Now minus 15 over 2 on both sides. I would now get 7x is equal to negative 15 over 2 plus or minus square root of 337 over 2, which that can even be combined to be negative 15 plus or minus the square root of 337 over 2. I have one last step to do, which is to divide by 7, but because of the fraction, I'll just multiply by the reciprocal, times 1 over 7 on both sides, which will give me the x I wanted, negative 15 plus or minus square root of 337 over 14. There are no i's, so these are going to be real solutions. And it's going to be negative 15 plus square root of 337 over 14 and then negative 15 minus square root of, I'm going to have to do this again. Negative 15 minus square root of 337 over 14. And that's correct. Let's try another one. Without solving the equation, state the number of solutions and why they're real or not real. So, okay, here we can just use the quadratic formula. We can use the discriminant. So we just got to, as long as the equation is equal to 0, which it is, identify A, B, and C. A here is negative 17, B is 6, and C is 12. So we can just use B squared minus 4AC and see what type of number we get. This would be 6 squared minus 4 times negative 17 times 12. 6 squared is 36. I have two negatives. Negative times negative is a positive. So then 4 times 17 times 12. And that gives me positive 816, which would give me 852. And being that that's a positive number, that means I have two real solutions. Here's another one. Here my A is negative 1. B is negative 1 over 3. And actually, I need to, because this is equal to 1, so I would actually have to subtract 1 on both sides to get negative x squared is equal to, negative x squared minus 1/3 x minus 1 is equal to 0. So C would be negative 1. So I would go B squared, which is 1/3 squared minus 4. A is negative 1. C is also negative 1. 1/3 squared is 1 over 9. There's 3 negatives, so I keep a minus, and 4 times 1 times 1 is 4, which I'll write 4 as 4 over 1. So this is 1 over 9 minus 36 over 9, which gives me negative 35 over 9. That's a negative number, so it means I'm not going to have any real solutions. Negative 35 over 9. And this is negative, so there are well, they don't give me that option, so what did I do wrong? Discriminant is negative. Two, okay, here we go. There's two non-real solutions. And then last one. Let's solve using the quadratic formula. We already have it equal to 0. So A is 1, B is negative 28, and C is 71. So X is equal to negative B. If B is negative 28, then positive 28, plus or minus the square root of B squared minus 4AC over 2A. 28 plus or minus the square root of negative 28 squared. Make sure when you square a number, you're always getting a positive, is 784. Then there's only one negative, so minus. Take a look at the negatives. If there's one negative or 3 negatives, then you would keep the minus. If there was, if either the 1 or the 71 were negative, meaning there would be 2 negatives in total, you can just turn that into a plus. 4 times 71 is 284. divided by 2. X is equal to 28 plus or minus the square root of 500 over 2. Now 500 is not perfect, but it isn't prime either, so you got to put that into a tree. So 500 is 2, 250, 2, 125. Then it should be 5, 25, 5, and 5. So I can bring out a 5 and a 2. 5 times 2 is 10. So we get 28 plus or minus 10 with a square root of 5. The 5 stays on the inside, divided by 2. And since 28 and 10 can both be divided by 2, we get 14 plus or minus 5 square root of 5. Those will be the answers that I put in. Five square root of 5 square root of 5, and then 14 minus 5 square root of 5. And that's correct.